So, okay, it's a pleasure to have Luca Ciambelli to talk about symplectic analysis of Null Raychaudhuri.
Can you hear me? Right. Well, let me start by thanking the organizer for the kind invitation to present my research. I know you're all tired from these long days of beautiful talks, but luckily I'm very loud and very noisy. So I will keep you, hopefully I will keep you awake and warm your appetite for the dinner. So in this talk, I will perform a symplectic analysis of the Null Raychaudhuri constraint. This is based on a recent paper I published with Laurent Friedel and Rob Lee and some work in progress. And in particular, what we're going to do, we're going to study the geometry, dynamics, and symplectic structure that is induced by gravity on null hypersurfaces, of generic null hypersurfaces. As it is well known since the membrane paradigm and even before by the works of Raychaudhuri and Amour, the Einstein equations projected on the null hypersurfaces give rise to intrinsic constraints that are called the Raychaudhuri and Amour constraints. And what we're going to see here, we're going to focus on the Raychaudhuri one and see that it actually has many facets. So it can be understood as a Carrollian conservation equation intrinsic to the null hypersurface. So conservation equation of geometric data and evolution, but also it can be understood as a stress tensors balance law between the different sectors of the theory. Later, we're gonna, using the symplectic analysis and the covariant phase space, we're gonna reveal a positive and monotonic boost charge in a particular notion of time, which only for non-expanding null hypersurfaces will coincide with the affine time, which we call here the dressing time. And toward the end of the talk, in the perturbative gravity regime, so in the weak gravity regime, we're going to see that the spin 0 and spin 2 degrees of freedom decouple, and there is an emerging beta gamma system that is related to null generators. And eventually, let me just point out that this talk is complementary to what Flanagan discussed this morning. In particular, in my talk, I will try to always use an intrinsic approach to one single null hypersurfaces, but we will see tools and dynamical equations that also Anna talked about this morning. All right. So let me start by reviewing quickly the geometry of null hypersurfaces. This is a long story, but here I'm going to use the more modern language. So it is now understood that a null hypersurface has a Carrollian fiber bundle structure, where the typical fibers are the generators on the null lines. And for simplicity here, I'm going to call these null hypersurfaces N. I'm going to assume they are three-dimensional, although it can be easily generalized to arbitrary dimension, as I have in mind the four-dimensional bulk. And also I'm going to regulate away from caustics. So on a generic null hypersurface, there are caustics at finite time. And I'm going to just regulate away and consider the smooth manifold between two caustics. And the information to retain are encoded into this Carrollian structure that is given by a vector field L, the Carrollian vector field, which is the tangent to the null generators. The generate metric QAB, and the condition that L dot QAB is 0, although L is nowhere vanishing. That is what enforces the degeneracy of the metric QAB. Now, in the language of fiber bundles, there is a Ehresmann connection that arises naturally. And here, this Ehresmann connection will be this K one form that is just ambiguously defined by the condition that L dot K is equal to 1. Okay, so this defines for me the Carrollian structure. The second fundamental form, or also called extrinsic curvature, is actually intrinsic on null hypersurfaces, and it's just given by the Lie derivative with respect to the Carrollian vector field of the degenerate metric. And it is such that its trace will contain the expansion, and its traceless part will contain the shear, and the shear plays a very important role as it encodes the radiative degrees of freedom. We're going to see that later. And here I use the Q with one index up and one index down, which is just the natural horizontal projector. So this projects to the space orthogonal to L and K. And in the following, I will use this projector to decompose all my tensors in the spaces that are horizontal and orthogonal. And now just a disclaimer, I will use the word horizontal or the word vertical or tangent to L indistinguishably, and the word horizontal or orthogonal to L indistinguishably. So the idea is that whenever I have a tensor, I can always decompose it in the L direction and orthogonal to L direction on the null hypersurface. Here, for instance, I draw a generic cut at constant null time. Okay, so another important ingredient is the Carrollian connection. On null manifold, there's no Levi-Civita theorem. So the Carrollian connection is defined by acting on the total volume form in this particular way, where there is this one form omega appearing, and as any other tensor in the theory, it's decomposed in the space orthogonal and vertical and horizontal. And the vertical part contains kappa, which from the bulk is the inaffinity that we saw this morning, and the horizontal part is pi a, the Ajicek connection. Okay, now let me briefly talk about dynamics. We introduced the null analog of the Brown-York tensor, written here, and now it has been shown that its covariant derivative is exactly equal to the Einstein equation projected on the null hypersurfaces in this series of papers. And here I just added the bulk matter, as if the Einstein equation were to be coupled to matter, they appear from this Navier-Stokes equation as a source, the matter term. Okay, and in particular, if I project along L and orthogonal to L, these constraints split in two. The projected to L part is the Null Raychaudhuri equation, the celebrated Null Raychaudhuri equation, and the orthogonal to L is the Damour equation, written here, which are evolutionary equations, therefore, for theta and pi. I introduce a new quantity here, mu. Mu is this particular combination of the inaffinity and expansion. It is called surface tension, and it is a very important ingredient in our theory that will appear throughout the talk. Okay, so to recap, if I take Einstein equation and I project them to the null hypersurface, this gives rise to, in particular, the Raychaudhuri equation for the vertical component. And this can be reinterpreted as a conservation law for a stress tensor on the null hypersurface itself. So this is a modern formulation of the membrane paradigm, but it extends generically not only to horizons, but to null hypersurfaces throughout the spacetime. Okay, now let me move to the symplectic analysis. One can introduce completely intrinsically again on the null hypersurface a symplectic structure written here. So how does that go? We take the stress tensor and we just again decompose it. So this tau A and tau AB are orthogonal to L. And then we just write something of the form, VEV delta source, as we're familiar from holography. Simply here, the source are the geometric data. And the geometric data are the degenerate metric Q and the Carrollian vector field L, and they couple to the momenta in the stress tensor. Okay, so this is a very natural symplectic form to consider, but actually it has been shown in a series of work that is actually what one derives from the bulk symplectic structure projected to the null hypersurface. And this is actually, if you consider the symplectic two form, which is just delta of this symplectic structure, is exactly what Flanagan wrote at the end of his talk. Okay, so one can consider the charges associated to diffeomorphisms along the null hypersurface, so diff n, and they just have the usual structure, equations of motion, plus a corner term, where C here is an arbitrary cut. To isolate the various degrees of freedom, we're going to decompose the degenerate metric into the areal form, which is just the area of the single cut, and the unimodular part. Then the measure decouple into the covariant measure and the coordinate measure, such that eventually the dynamical equation can be written in terms of the spin zero data that are written here, the surface tension and the areal form, the spin 1 data, Carrollian vector field and Ajicek, and spin 2 data are the unimodular part of the degenerate metric and the shear that contains the information on radiation. Okay, now we want to focus only on Raychaudhuri. We don't want to talk also about Damour. And since Damour is evolution equation for the Ajicek and the spin 1 sector, we want to decouple the spin 1 sector and focus only on spin 0 and spin 2. And to do so, we notice, first of all, that it's enough to consider diffeomorphisms along L, so the time reparametrization diffeomorphism, so we set y to 0, and that L itself is defined modulo internal boost, because the condition L dot Q equal to 0 is invariant under this transformation. Okay, so we can use this internal boost to actually dress the diffeomorphism. So in particular, the spin 1 data were the Agi check and the delta L. So we want to set delta L to 0. First of all, we notice that thanks to this condition here, delta L can be written as proportional to L itself. But then we notice that the time reparametrization and the internal boost act in a very similar way. And actually, by choosing to dress the diffeomorphisms with the particular internal boost given by this, we can always consistently set delta L to 0. And the phase space in which this is achieved is going to call the primed phase space. And in this prime phase space, as I'm going to show now, the spin 1 sector completely decoupled, and I have my Raychaudhuri constraint and the spin 0/2 sector. Okay, so in particular, since now L is constant throughout phase space, I can choose conveniently to a notion of time coordinate, null time coordinate V. And then the Raychaudhuri constraint written in this null time coordinate have this form. Okay, where first was written in terms of the expansion. Okay, then the time reparametrization charge can be computed from the equation below, from the equations above. It contains the Raychaudhuri constraint plus a corner term, which has this form, which is going to be very important for computing the boost charge later on. Okay, so these are the two main equations. Notice the Raychaudhuri constraint is going to appear a lot later on as well. And now finally, I can talk about the symplectic structure. So there was a term proportional to delta L that decouples because I set that to 0. So this is just the spin 2 data and the spin 0 data, but they actually couple non-trivially together. All right, and we want to compute the Poisson bracket on this. To do so, we notice that sigma has some constraints because it's symmetric and traceless. So the way to decouple this and fully invert this symplectic structure is actually to employ the Beltrami differentials, which is now very specific to 3-dimension for the null hypersurface and therefore 2-dimensional cuts, because a unimodular metric in 2-dimension has just 2 independent components and therefore can be parameterized fully in terms of the Beltrami differential zeta and zeta bar. Okay, so in this case, by defining the Beltrami differentials and introduce the specific propagator, where this is just the delta function and this is the heaviside theta function on the null time, we can find the Poisson brackets. First of all, the spin 2 sector is just the non-commutative usual sector like this. The spin 0 mu do not Poisson commute with the spin 2. So there is a mixing between spin 0 and spin 2 sectors. And the spin 0 sector alone is just the Heisenberg pairs. Whereas the mu itself now is actually not commutative in phase space due to radiation, which is the derivative of the Beltrami. So let me make a couple of comments because this equation might be a bit dense. So the first comment is that this is ultra local on the cut. On the fixed V cut, there is a delta here. So if I take just 2 points on different generators, they just Poisson commute. But it is not ultra local on the null generator itself because of the heaviside here. Okay, so there is this structure that is non-commutative on null generators. And very importantly, mu here is a crucial field. It is what allows for the non-perturbative mixing between the spin 0 and spin 2 sector, again, at the non-perturbative level. All right, so now let me switch gear and talk a bit about the boost charge. And for doing this, we want to introduce the notion of dressing time. And the dressing time is achieved by setting the surface tension to 0. But as we just saw, the surface tension is actually something that appears and propagates throughout the dynamical equations. So we cannot just set it to 0. It would be an assumption on our phase space and on our theory. So actually what we need to do is to trade it with another dynamical variable. And to do so, we perform a time reparametrization here, generated by this function V, which is always accompanied by a internal boost on my prime phase space. And doing so, my fields transform in this way now, where I haven't showed that detail, but mu is a boost connection, so it receives an extra shift. And the constraint by construction, this is a good cross check, it should be covariant under this transformation. And then now we can trade the surface tension by the generator of the diffeomorphism itself, V. Okay, so the dressing time is achieved by trading mu with V, okay, which is just this equation here. Okay, and now just a little aside, which is important, mu, remember, was equal to kappa plus theta half. If I have a non-expanding horizon, the inaffinity is equal to the surface gravity, and therefore if I set, and theta is 0, and therefore if I set mu to 0 is equivalent of setting the surface gravity to 0, which is the condition that brings me to the affine time. But on generic null hypersurfaces, this notion of time is different from the affine time, because I'm setting kappa plus theta half to 0 and not kappa to 0. Okay? Good. Now, as I was saying, we trade the mu with V. So we render V part of the phase space. So this was our canonical symplectic 2 form. And therefore now, using the dressing time, I have here these extra shifts in delta V. And by do so for all our fields, I spare you the details. The final result is that the spin 2 structure just get dressed in the right way, but the spin 0 sector mu and theta is replaced by V delta C, where C is the Raychaudhuri constraints itself. Okay? So the main result is that in dressing time, the constraint is the symplectic pair of the dressing time. Okay? So I evolved throughout the null hypersurface with my dressing time V, and the symplectic pair is the Raychaudhuri constraint itself. Okay? Okay, now I'm going to use this dressing time, and in particular, the Raychaudhuri equation in dressing time, mu tilde is equal to 0, so it's just equal to this, okay, where I have some matter, and the charge is just equal to that. And now I'm going to restrict, this is just a time reparametrization charge, so it's general, I'm going to restrict it to a particular generator, which is the boost. So it's a boost whose fixed point is V equal to T, okay, so it's just V minus T partial V. So this cut CT is the one at V equal to T. Okay, it looks like that. And if I have a bulk spacetime and my null hypersurface is here, it just looks like this one here. Okay, and in particular, at the fixed point of the boost, I can compute this charge, and this value is just the area at the cut, which is obviously by construction positive and strictly positive because I'm away from caustics. Okay, then if I then consider the boost charge aspect, so is integrand, and I compute its first V derivative, it's just proportional to dV square of omega, then I can use the Raychaudhuri equation in the dressing time frame to replace that by sigma square plus the matter. And therefore, you immediately see that this guy is positive, and assuming the null energy condition, this guy would be also positive, and therefore, the boost charge on shell is just monotonic. Its first derivative is strictly positive. And this boost charge is derived from the symplectic structure. Okay? So this result, I want to insist that holds even when expansion is present. Okay? And it's actually what I'm working on these days also is try to relate it to the notion of dynamical entropy. So to show what the notion of dynamical entropy is, let me just take the difference of two boosts, the finite difference. Then this has an area law relationship here, except that there is an extra term, which depends on the expansion at the final time, for which I take the difference. And now this is has been advocated, as far as I can tell, 20 years ago, but also very recently, to be the correct generalization of the notion of entropy for dynamical horizon from the phase space. And actually, I've been told that there are two different groups, Bob Walde and Zhang, and Visser and Yan, that are working on this notion right now. And we see that here, I'm proposing that it comes from the boost charge on the phase space that I constructed from Null Raychaudhuri in dressing time and in the primed phase space. Okay, good. So in the remaining 15 minutes, something like that, I'm going to talk very briefly about the beta gamma, and then I'm going to offer some conclusion. Okay, and for the beta gamma, what I'm going to do, I'm going to perform a weak gravity expansion. So now this is, for the moment, I haven't studied the most general weak gravity expansion. I've made a set of assumptions that I'm going to mention to you because I just wanted to highlight a result, and it's part of current investigation to put it into a more rigorous framework. So the weak gravity expansion is just the expansion in this epsilon, so in G Newton, and all my fields are going to have an expansion in powers of epsilon. So the first assumption I'm going to make is that the areal form will have a classical value omega 0 plus an order G expansion, where this field gamma appears, plus a bleeding order. And there could have been an order epsilon, so a linear to epsilon. This is the first assumption. I'm going to justify it later on, but it is an assumption at this stage. And then I'm going to put the perturbative gravitons inside the Beltrami differentials. Why? Because if I take the form of the matrix, the Beltrami differentials are exactly a generic diffeomorphism starting from the round to sphere. So if I put here an order epsilon graviton, that's exactly what I expect it to do. It's going to take the sphere and it's going to make it wiggle at first order. Okay, so that's X, capital X here will include information about the perturbative graviton. Also, they are into the spin 2. So it's important that I choose the spin 2 fields here. And then if I do that, the sigma squares that appear in Raychaudhuri is actually order epsilon square. And another assumption I'm going to make, I'm going to choose that my surface tension has a 0 order plus the next correction is far away in the expansion. And to do that, essentially what I'm saying is that order by order for the first two orders, I'm going to go into the dressing time. That's this assumption here. Now, if I take the Raychaudhuri constraint, this assumption here in the absence of order epsilon and this assumption here are a solution particular, not the most general solution, of the C1 here, the constrainted over the epsilon, which is not there. I've already solved it by my assumption. So the constraint has this generic form as an order 0 plus an order epsilon square. And actually the order 0 just contains the spin 0 factor. There's no spin 2 and there's no matter here. And so I'm gonna also do a conservative solution here, which is just non-expanding null hypersurfaces. So the areal form is constant in V time at order 0, which is the typical framework for this perturbative expansion. And then the next non-trivial order is the C2, which now has this particular form. Okay, so this is the spin 2, this is the spin 0 sector, and this is the matter that now appears non-trivially only this order. And notice that if I introduce, well, the spin 2 is obviously as a stress tensor like this, but if I introduce a spin 0 stress tensor like this by hand at this stage, I just realized that the second order in the constraint is actually a stress tensor equality for the three sectors of the theory, where now I've introduced the spin 0, which is the stress tensor associated to the geometry. Okay, now I want to give further evidence why this is the right result. And one evidence is that I can introduce this spin 0 stress tensor because at the right order in the Poisson bracket, so I didn't show you all the details of the perturbation, but you can just take 10 slides ago and just perturb in G Newton using the expansion of the previous slide, the spin 0 and spin 2 sector decouple. Okay, so non-perturbative in G Newton, spin 0 and spin 2 sector talk together in the symplectic structure and in the Poisson bracket, but at this order in perturbation, they don't. And indeed, this is the same as saying that the spin 0 stress tensor do Poisson commute with the spin 2. Okay? Then, let me make some further comments. So if I take the spin 0 sector, which is now completely decoupled and work only on this, the Poisson brackets are written here. So in particular, also mu becomes a commutative field. And this is very important for what I'm going to say. Then if I suppose I just canonically quantize and I consider Weitman-Green functions, the OPE I get from here with the right epsilon prescription is this one. And I just remind you that the stress tensor is this one. And now this one notice that per point on the cut, so if I forget about this delta 2 and I assume my fields are only function of V for the moment, so per point on the cut, this is actually exactly equal to the OPE and stress tensor of a curved beta gamma system. Okay, where the OPE between beta and gamma, if I consider beta one form, is this one, and the stress tensor is this one, and therefore this analogy assume that my field surface tension mu is equal to the component of the one form beta, which is a connection. So this is actually a good identification, and it gives me a quote unquote prediction. At this stage, I'm proposing it as an analogy for the moment between the determinant of the top form in the target space omega that appears here in the beta gamma and my field gamma here. Okay, and so the message to retain is that there is an analogy here that in perturbative in the weak gravity regime, the spin zero geometry completely decouples from the spin two, and it behaves like a beta gamma system on each null line. And this is really true all in perturbation because non-perturbatives, my mu field do not commute due to the spin two sector. All right, I think I actually am ready to say some final words. So I'm in perfect time. Let's see, 8 minutes or something like that. Perfect. We can have dinner early enough. Okay, so let me just recap what I did here. First of all, I showed that the Raychaudhuri constraint is a Carrollian conservation law. This goes back to the membrane paradigm, but reformulated in a more modern language. It also immediately showed that if I want a fluid interpretation, it's not a non-relativistic or Galilean, but is a ultra-relativistic, so it's a Carrollian fluid, and this echoes with previous works on the topic. I then perform the symplectic analysis and show the kinematical Poisson bracket. And in particular, I insisted on the fact that non-perturbatively in G Newton, the spin 0 and spin 2 sector of the theory couple together. And this is actually what renders the mu field in the spin 0 sector non-commutative. So it's a Poisson non-commutative field due to the fact that there is spin 2 radiation, because on the right-hand side, there was partial V of zeta and partial V of zeta bar. Okay. Then I introduced the notion of dressing time. This is a generalization of the notion of affine time. It coincides with affine time for non-expanding hypersurfaces, but otherwise there are two different notions of time. And I've shown that in that notion of time, the boost charge on my prime phase space is positive and monotonic. Okay, here again, I was completely classical. I assumed the null energy condition, and I just used the Raychaudhuri constraint in dressing time. And the fact that I was in dressing time was fundamental because the extra term that depends by mu has the opposite sign. So if I would have just used the Raychaudhuri equation in an arbitrary time frame, I would not have monotonicity. Okay, this I hope it was clear. I then perform a perturbative expansion with a set of assumptions, and I just notice at this stage a very suggesting analogy between the physics of the spin 0 geometric degrees of freedom and a beta gamma system on the null line. And in particular, I want to stress that this stress tensor I've introduced and this beta gamma is actually about the geometry itself. So here I'm not talking about a perturbative field on some background. I'm talking about how the background itself behave on the null generator. And okay, let me finish with some future directions. So the first thing that I'm working on these days is the obvious generalization to include Damour. So to include the equation that was related to the time evolution of the Ajicek one form, and of course, therefore, reintroduce the spin 1 in the theory. And this requires the notion of a more sophisticated dressing, but this is very interesting. Another direction is to understand better which set of assumption and more rigorously whether this analogy with the beta gamma system is not just an analogy, and there is something perhaps that one can say in the perturbative quantization, so in the weak gravity regime, in relationship to all the very thriving results recently in von Neumann algebras for gravity. And finally, the boost charge that I have and the notion of dynamical entropy could be very interesting to explore in relationship to the modular theory, and perhaps it might provide an arena to study from the phase space and adding quantum effects, and therefore studying the quantum focusing conjecture. And right on the 5 minutes time, I'll stop here. Thank you very much.
The resting time, I was wondering if you do what that module diamond. It's not the half-life time.
Right, right.
The question is,
I actually haven't checked that. There must be something that's not a complicated thing to do. So I will try to have a look at that and let you know as soon as possible. But yeah, I suspect it will be related to some nice generator inside my diffeomorphisms. Yes.
So just clear, it's not possible to vary that elements of the way that
Affinity vanishes.
the unity happens.
Okay.
Right. So sorry, let me rephrase. So when we create
Right. Right. So let me go back to the original. Oops, I went too far. To the original symplectic structure here. Here. So this is. So here I'm just thinking of what you would do naively when you define your stress tensor as delta S over delta G, but except that I don't have G, right? My geometry is really L and Q independently, right? Because Q is degenerate. So I really have to tell you both L and Q to determine the null hypersurface geometry. Okay, so here I'm treating L as, if you want, part of the basic fundamental geometry, which it is. Well, I mean, if I write down the metric, if I write down this metric, for instance, well, let me do for the full non-unimodular. This you don't know it's a null hypersurface. You don't know that this is a null hypersurface, or this is a null manifold, or this is a Carrollian manifold, or a fiber bundle structure. You really need both separately, right? And that's why I'm choosing L. It has a symmetry. It has the internal boost that I defined. So indeed, what I'm choosing, and this is related also to the way Ianna this morning was presenting the set of initial value problems for the null cone, it has an internal symmetry, which is the shift symmetry, right? Because the only condition that defines it for me is that it must do that. And of course, each of these guys multiply, if the metric doesn't transform in some weird way, would still satisfy that equation. So it's not any L. I mean, I'm choosing a representative in that conformal class of symmetries, but actually I'm using that internal boost symmetry. I called it boost because it's a shift in the, it's a rescaling in the null vector. So it's a boost that I'm choosing a representative, but I'm using that symmetry later on for the prime phase space. Does that help?
it helps, but I think we should talk.
Okay. I would be very happy to talk further about it. I'm not sure I really got exactly the question. Yeah, so that's a very good question. They were written here, but I just didn't expand on those. So let me just give you the formula. Here they are. So here I haven't choose that my diffeomorphism of the null hypersurface is just time reparameterization. So if I insert here xi, which is generic, so fl plus y, where y is orthogonal, then I can compute the charge associated to this y, and the charge associated to this y is actually just equal on the cut on shell of Damour in particular, ya pi a. So pi a, which is the Ajicek connection, is exactly what plays the role of the angular momentum at finite distance. Yes and no. So in the primed phase space that I've used, q prime y is equal to qy actually. But this is because I'm just dressing the time reparameterization with the internal boost. On the other hand, when I will talk about Damour a bit better, I will have to be more careful about that, because that I was only dressing the time reparameterization because I was only caring about the Null Raychaudhuri constraint. But if I want to care about Damour and I need to talk about this charge, I have to be more general, and actually I have to dress with more symmetries. We can discuss about it later. And then the q prime on this dressed phase space will not be the same. But on the phase space I've introduced, this prime is not a problem. You can put it or remove it. Sure. Question? Is the third of the future direction. So I'm not sure that you have the right to ask that question. No, I'm kidding. I'm kidding. No, this actually will follow the discussion I had with Aaron Wall. And we just noticed that there are the premises to talk about that. Oh, sorry, I don't want to start playing too much with the slides. So let me just say it in word. So this boost charge that I have is monotonic, but the bound, so its first derivative is greater or equal to 0, and the bound equal to 0. It satisfies what it is satisfied on the shearless, so no radiative from the spin 2 sector, and the vacuum matter sector, where the stress tensor for the matter vanishes. And this is one of the premises that discussing with Aaron, you need to have in order for this to be a good candidate for be some sort of modular flow. And now I don't want to make any big statement because indeed I don't know, but what I would like to understand is whether we can use, okay. So one thing that, and the reason why these two actually go together is that the matter that I have to couple, it should be perturbatively coupled in order to be in the framework of the quantum focusing conjecture. And right now I haven't done that. So for instance, that's already a reason why I cannot tell you that much, but there's definitely something quote unquote more general here than the framework in which the quantum focusing conjecture is stated. So I want to try to see whether if I go with all that the assumptions needed to go there, and I go there, I can say something more. That's the only thing I can say right now. No, thank you.
You at some point you had a formula for entropy.
Yeah. Yeah, that was actually still again my boost charge.
Yeah. So so can you say a little more? So I guess so here we're just in Einstein gravity.
Yeah.
Correct?
Yeah. Yeah.
So entropy in some sense should just be area.
Well, that's true if you consider a non-expanding horizon, or if you consider an expanding horizon, which is event horizon, so it's teleological. So at the end of the day, where you compute at the limit to infinity, there's no expansion. This is exactly true here, because this is the expansion of the endpoint. Yeah. So if you just take an event horizon and you assume some dynamics, but you assume that it's settled down, yeah, then you use that as an anchor to compute that. And indeed, when theta at the endpoint, the expansion at the endpoint, the end cut is 0, this is exactly the area law that you would have for the horizon. So this is a generalization when you consider either a finite distance point on the horizon or just a generic null cut, null hypersurface. So for a generic null hypersurface, you expect expansions everywhere, but also more importantly, you expect the formation of caustics at finite time. So you really cannot say, oh, I'm just gonna go far away where the expansion vanish. So this would be the correct generalization of the entropy law when you have dynamics at the endpoint.
But should I expect all of it to be a delta? Is alpha not great?
No, but
That's what I'm trying.
no, sure. But what I'm saying is that when you take the finite difference of two cuts, for having the area law, you have to assume that on the second cut there's no expansion. This is directly a consequence of the Raychaudhuri constraint.
I mean, maybe I can ask differently. So does this entropy, or should I expect this entropy to obey laws of thermodynamics? Like, does this obey the second law, or this law, that?
It would, in the framework in which you establish that laws, it would exactly obey.
Yeah, but you said it's a generalization, so that's why it's so when it's not just equal to the area, you know, and just reduced to the Hawking theorem and so on. Does it describe an entropy that should obey thermodynamic laws?
It does describe thermodynamics laws. So for instance, the right-hand side here is positive or equal to 0 by construction. Yeah. Okay, so it does satisfy some laws, but they are modified, the laws themselves. And there was a question, I don't know if I interrupted.
I mean, I don't know exactly the same. It surprisingly does obey a second. There's two different.
Yeah, so
that's partially it. Is
there
a first law? I think so.
So I had so I had a discussion with Antoine that confirmed that what they are after is a formula which is exactly like this. Now I don't know, I don't think they derived it from the phase space, but yeah, exactly. Oh, did I interrupt? There was a comment. Okay, sorry about that.
Luca again.